No audible on YouTube. No audible on YouTube. So can you hear me on Google Meet?
Yes, sir.
Yeah. So these phase-space trajectory questions are a bit frequent in CSIR net exam, as you might have already observed. So how do you define phase space? It's a what you call position momentum space. Am I right? Simply. So now, suppose if you take particle moving in one dimension. Okay, speak up. A particle, one particle moving in one dimension. Am I right? Speak up. So that phase space will be defined by position and momentum. Can I say x and px? Only one position, one momentum. Am I right? One particle moving in one dimension. Okay. Suppose so that's why this phase space dimension will be 2 actually. Okay, a particle moving in one dimension. What is degree of freedom? That's equal to 1. Okay, speak up. Phase space dimension will always be double the degree of freedom of the problem. Okay, speak up. Suppose if a particle, okay, moving in so 2 dimension, in that case degree of freedom of the particle is 2. Okay, the phase space dimension will be particle moving in 2 dimension means we need two coordinate to explain. Am I right? X and y. Along with that one, in phase space we add moment also. Okay, that's a complete description of the particle. Am I right? Position as well as momentum. Okay, if you know position and momentum at any instant of time, positions and momenta. Can I say like this? Okay, at any one instant of time, then you know everything about the system. Okay, you know any quantity in the future. Any quantity at any instant of time. Okay, speak up. So that's why. So phase space becomes a bit important discussion. Px, py. Fine. Speak up. Now, if you want to draw phase space trajectory, you can, only draw 2 dimension. Am I right? Look at here. Okay, lowest degree of freedom is 1. Am I right? What is the next higher degree of freedom? 2. For this one, phase space dimension became 4. Isn't it? That's why most of the case they are giving problem on this one. 1 degree of freedom problem. Okay, so you just have to draw the phase space trajectory. Okay, speak. So that phase space trajectory. Okay, so what we do is, okay, usually when you solve the problem, okay, you will find x as a function of t. Am I right? And px as a function of t usually when you solve using Newton's second law or something. Okay, so then if you draw a trajectory at different times, suppose this is x here, this is px here, at different time these values will have different values. Am I right? Pick up those. Those will be these points, suppose. Okay, at different time. Okay, x and px are taking different values. Okay, speak up. So now suppose if you eliminate time from this equation, if you find suppose p as a function of x, okay, or x as a function of px, what do you mean by eliminating time? That means you are what are these points? These are the point that our system so that our system, okay, acquired in the phase space, okay, at different instant of time. When you eliminate time, it became time independent picture. Am I right? That means you have collected all of these points at one instant of time. Okay, I mean, if you have a relation of, okay, px as a function of x, okay, can I write like this? Px as a function of x, okay, that means, I mean, you have to eliminate time here, am I right? You solve for time in one of the equation, you substitute into other, you will get x and px relation, isn't it? Speak up. What do you mean by eliminating time? Eliminating time means, okay, these were the point that our system is going to acquire at different time. Okay, so you made it time independent, means you collected all of those points at one instant of time. Okay, speak up. So that we call it as phase space trajectory, and that trajectory will have one direction also. Okay, direction means what do you mean by this direction? That means at one instant of time, if our system is here, okay, if this is the phase point of our system at one instant of time, as time evolves, the next time it will be here, it will be here, like this actually. That's what you call phase space trajectory direction signifies. Okay, speak up. Now, okay, how do we draw this phase space trajectory? Am I right? I mean, so they didn't ask question on four. I mean, how do you draw four dimensional? How do you draw four dimension? Isn't it? You can't draw. So that's why they restricted question to one particle moving in one dimension. Okay, speak up. So now, how do you draw that one? Okay, how do you draw phase space trajectory? First thing is, most of the case we are discussing conservative system. Am I right? Speak up. Even though there may be some system where energy may be dissipating or something, am I right? Friction or something. Okay, but we can write one expression Hamiltonian. Okay, speak up. X comma px. That's equal to. Can I write? I mean, I don't have to write px here. Why? I mean, in one dimension, I just write x and p. Is that fine? In case of one dimension, okay, I'll just write x and p because I don't have to write px here. Am I right? Px means when you have two dimension, px, py, like that. Okay, speak up. I'll write like this. Okay, x comma p. Okay, what is this one? P square by 2m. Okay, plus v of x. Am I right? In case of conservative system, speak up. This is the energy, isn't it? So p square by 2m plus v of x, okay, that's equal to energy. Now this itself is the relation between p and x. Check this out, isn't it? That equation itself has, I mean, okay, phase space trajectory means you have to find the relation between p in terms of x, isn't it? Pick up. So this expression itself have that relation. That okay? Speak up. Energy. Sometimes we will have some system. We'll see if any frictional force comes, energy keep on decreasing. Am I right? On that basis, again we can again use the same expression, okay, to draw the phase space trajectory. Fine. Speak up. Now we'll start with this harmonic oscillator. Okay, from the harmonic oscillator example, we'll grab all of the idea. Okay, we'll collect all idea from harmonic oscillator. Then we will start applying for other problem. Okay, speaker. So harmonic oscillator. I mean, you have a spring mass problem. Okay, speaker. So spring of spring constant k. Okay, mass m here. Okay, so at when it is at rest, it is at x equal to 0. Okay, if you dragged it by a distance x and if you leave it, it will start oscillating. Am I right? Speaker. This everything does matter here. We'll see. Speak up. Suppose I'll take this one as positive x-axis. This is my origin. Is that okay? Origin x equal to 0. This is my positive x-axis. Okay. Speak up. Now, okay. I mean, this is one of the system that we are studying here. Okay. What defines the system in this equation? Kinetic energy, non-relativistically, it's always p square by 2m. Okay. This v of x that defines the system. Am I right? I mean, any conservative system you take, v of x defines the system. What is that v of x? V of x is equal to half kx square. So that, I mean, in this case, okay, v of x, I mean, if you say linear harmonic oscillator, first what you write v of x. That's equal to half kx square, like that. Fine. Speak up. So then look at here, your equation is p square by 2m plus v of x is half k x square. That's equal to energy. Okay, I mean, if it is frictionless, okay, if the table is frictionless, okay, when
Sir,
huh,
yes, screen is not visible, sir.
screen is not visible, why it is going off? Fine.
Yes, sir.
Yeah. So now, so suppose if it is frictionless, okay, then this energy is constant, am I right? If it is frictionful, that energy keep on decreasing. Okay, we'll see this one. Okay. Now this expression itself have P and X relation. Okay. So what you have to do? You have to manipulate that one. Okay. Speak up. So I mean, I'll start with this one. Usually we write. I mean, okay. Just check this one. X square by, okay, 2e by k, under root the whole square. Fine. Speak up. Plus p square by root of 2me the whole square equal to 1, isn't it? What is this one? This is an equation of ellipse, isn't it? So this is an equation of ellipse. P here, x here. I mean, so that's why I wrote x first. I mean, whenever we write equation of ellipse, we write x square by a square, y square by b square equal to 1. Okay, so that's what I have written. Okay, speak up. Now that if you write x square by a square plus y square by b square equal to 1, y means p here. Okay, so usually semi-major axis is a, am I right? I mean, it all depends on whether a is greater than b or b is greater than a. Okay, whether your semi-major axis is horizontal or vertical. Okay, but let us assume that semi-major axis is horizontal. Okay, speak up. I mean, it all depends on these quantities actually. Okay, speak up. Now look into this one carefully. Speak up. Now, can you point out these points here? This is 0. From this equation, that root of 2e by k. Am I right? Speak up. What is this one? This is plus root of 2e by k. This is, yeah, semi-major axis. Am I right? This is semi-major axis. This is total major axis. Okay. This is minus root of 2e by k. Am I right? Speak up. Now, I mean, what is this one? Plus root of 2m into e. Okay. This is minus root of 2m into e. I mean, even if you take this equation, if you put x equal to 0, p will be solved to plus or minus root 2me. Can you see this one? If x equal to 0, there are two p values, isn't it? That's what it is saying. Okay. Again, if you take this equation, if you put p equal to 0, x has two values. Am I right? Plus or minus 2e by k. Those are, I mean, when p equal to 0, you have x two values. Okay. Speak up. Anyway, in this case, it's quite simple. Now, observation that you make is, okay, if you keep on increasing the energy, how do you increase the energy here? Okay, this is how I wrote the energy, okay, as a variable, I mean, two variable combined, okay. So what does energy depends on? Energy depends on amplitude actually. I mean, for a given spring, for a given mass and all. Okay, how do you find that one? Speak up. At extreme position, okay, your energy is equal to potential energy, am I right? Half k a square. Suppose a is the amplitude. Can I say like this? Half kx square is the potential energy. At extreme position, no kinetic energy. Energy is equal to potential energy. At extreme position, I mean, its amplitude, I mean, x value will be amplitude. Am I right? That's how I quickly wrote the, what you call, energy expression. Energy depends on the amplitude. If you increase the amplitude, you have higher energy. Okay. Now you can see here actually, this itself is the amplitude actually. Are you going to find? Check this out. Solve it for a 2e by k, root of 2e by k. Speak up. Now, if you increase the amplitude or if you increase the energy, you can see here, your semi-major axis depends on energy. So it will become bigger and bigger ellipse. If you decrease the energy, it will become smaller and smaller ellipse. That is one observation you make here. Okay, I mean, this is very simple problem, but this observation, I mean, we can apply in many other problems. Fine. Next thing, what they can ask is, Okay. Yeah. As energy decreases, this will shrink. Okay, speak up. What is the stable equilibrium position here? There is x equal to 0. Okay, it will shrink at x equal to 0 actually. Phase space trajectory will shrink to the point of stable equilibrium. Is that okay? That is the one idea that you can remember. Suppose if this stable equilibrium shifted, phase space trajectory would also be shifted actually. Anyway, we didn't have that kind of potential. We had simple potential, half kx square. Am I right? If you draw that potential, okay, what would you see? If you draw the potential, I mean, usually I prefer drawing the potential and then drawing this phase space trajectory. Okay, if I draw the potential, hmm, if I draw the potential, okay, speak up, parabolic, half kx square. I think I may need to draw it quite bigger here. Half kx square, okay, v of x as a function of x. Fine. Speak up. So then this is your stable equilibrium, right? Potential minimum is a stable equilibrium. Okay. You can see here, if you keep on decreasing the energy, okay, I mean, usually, I mean, when our what do you call that mass is oscillating about this x equal to 0, if you keep on decreasing the energy, it will come to rest at this location, am I right? Or if you give some damping, okay, speak up, it will ultimately come to rest at this location, am I right? So like that, if you keep on decreasing the energy, you can see here, okay, I mean, you can see this depends on energy. If you keep on decreasing energy or keep on decreasing the amplitude, this phase space trajectory is going to shrink to the point of stable equilibrium. Okay, that is another observation. So next one is, speak up, direction. Direction means what? Okay, these all are points that our system is going to pick at different time, different instant of its what do you call motion. Okay, speak up. But if our system is here at one instant of time, whether in next instant of time, whether it moves here or here, isn't it? Okay, that is the question. Okay, that's why that phase space trajectory direction is also important. Now for the direction, you need to go for what you call the system, or sometimes this so potential. Suppose, okay, suppose if you drag, I mean, look at here. If this mass moves along positive x direction, then its momentum is positive. Now look here, that can be happening like here also. From suppose this extreme position, mass, I mean, its x location can be negative, but it may start moving along positive x direction. Whenever mass moving along positive x direction, its momentum is positive. Whenever mass moves along negative x direction, momentum is negative. Okay. Now let me start with this one. Okay, what is this one? This is one of the extreme position. Am I right? Right extreme position. If you drag the mass to that right extreme position and if you leave it, what will happen? It will start moving along negative x-axis. Its momentum will be negative and increasing, isn't it? Why? I mean, from here, okay, if you drag it and if you leave it, it will start moving along negative x-axis with increase in momentum. Am I right? Speak up. Why? Because when at that position it has zero momentum. Okay, its momentum keep on increasing, will have maximum value at mean position. Again, momentum keep on decreasing. Okay, momentum will be zero, isn't it? But it is moving along negative x-axis. Speak up. So that's why if you start from this extreme position, okay, look at here. In the next point, I mean next instant of time, its momentum is negative and increasing, isn't it? Then negative and decreasing to zero. Are you getting my point? So that's why this is the direction of phase space trajectory. I mean, you can start with any situation, or you do one thing. You drag this mass to this extreme. This is x-axis only. Okay, speak up. You drag this. I mean, this axis is momentum. Okay, so you drag this mass to this extreme position and you leave it. What it will do? It will start moving along positive x-axis, positive momentum. Momentum will increase when it comes to mean position. When it goes to other extreme position, momentum will be zero. Okay, this is how you have to find the what you call direction for the phase space trajectory. It says that at any instant of time, if our system is here, at next instant of time, it will be here, like that. Fine? Speak up. Now, what I will do is, any problem? Why? Now, we better to make some observation. Am I right? Speak up. Some observation means, okay? Suppose what I will do is, okay? Give me a minute. So what we can do is, okay, before proceeding, okay, so we can grab all of this information without drawing that spring mass at all. What defines the system? Okay, I mean, I said this one to be used, am I right? P square by 2m plus V of x, that's equal to energy, isn't it? What defines the equation? I mean, if energy is conserved, V of x, isn't it? Once I write V of x is equal to half kx square. Okay, with whatever the experience we have, we can fully draw the phase space trajectory. Not only in this problem, okay, in any other problem. Suppose if I draw this half kx square curve here, okay, speak up. Fine. V of x, that's equal to half kx square. Okay, speak up. So now I'm going to decide some energy. Am I right? I mean, our system will have some energy, isn't it? This energy E. Okay, speak up. So that energy we prefer writing on this one. Okay, speak up. We prefer drawing that energy on this one, on the potential curve. Okay, assume that potential curve is symmetric. Okay, if this is the energy of the system, okay, then look at here. These are its extreme position where energy equal to potential energy and kinetic energy is 0. Can you see here? Or particles cannot go here because at this location energy is lower than the potential energy. If energy is lower than the potential energy, see this expression from this one, kinetic energy, that's equal to energy minus potential energy. If V of x is higher than E, kinetic energy would be negative. That won't happen. Okay, this is the classically allowed region. It will oscillate between these 2 points. And those 2 points you can see here, it's a symmetric curve. They should be symmetric. Am I right? Speak up. You can guess here. Potential minimum, that is our stable equilibrium. Am I right? This is our stable equilibrium. It's going to oscillate between minus A to plus A. How do you find minus A and plus A? By equating energy to potential energy. I mean, how do you find this location on x-axis? Okay, speak up. By equating E is equal to half k A square. Fine. That A is nothing but root of 2e by k plus root of 2e by k minus root of 2e by k. Okay, speak up. Now look at here. So below this one, okay, below this one, we prefer drawing the phase space trajectory. Okay, speak up. Below this curve, okay, let us merge this x-axis. Okay, fine. Let us merge this x-axis. Okay, what we shall do? P here, x here. Okay, let me take it like this. Okay, this is my minus a location, this is my plus a location. Fine. Speak up. Now we shall draw our phase space trajectory like this, isn't it? At these two position, momentums are 0. Okay, at mean position, momentum is maximum. It's ellipse, we already know that one. But its x values are restricted to these two, isn't it? That's why we shall merge this x axis. Only y axis here it is v of x, here it is p. That is the only difference. Okay, speak up. Let's see this one. Fine. It will be like this. So this is our what you call plus A. This is our minus A. That is our amplitude. Fine. Speak up. Now you can see here, if you keep on increasing the energy, what will happen? If you shift this one, okay, speak up. This amplitude is increasing. If you keep on decreasing the energy, this amplitude is decreasing. If you keep on increasing the energy, this will be bigger and bigger ellipse. If you keep on decreasing the energy, it will be smaller and smaller ellipse. If again energy becomes potential minimum, okay, it will be at rest. That is the center point of our phase space trajectory. Fine. Somehow you can argue here, okay. And what I am expecting here is, okay, here also, suppose if you need direction for the phase space trajectory, okay, speak up, then what you have to do is you start with any point here. Suppose if you start with this point, at this point particle is at rest, am I right? At this point, but it is experiencing force, isn't it? At that extreme position, I mean, how do you define force? Minus dv by dx. Speak up. Now here dv by dx is positive at this location with one more negative sign. That means it is experiencing force in negative x-axis. It won't be at rest over there. Am I right? It is experiencing force in negative x-axis. It will start moving. When it comes to mean position, what is dv by dx? 0. Force is 0, but it has already gained the kinetic energy because of that moment of what is that? Because of that inertia. Okay, it will keep on moving. It will go to next extreme position. Am I right? This information is sufficient to talk about direction. Okay, you started with this one. I mean, at this location, it is having force along negative x-axis. Okay, so that's why it will start moving along negative x-axis with increase in momentum. So that's why from here, it goes here, isn't it? I mean, momentum increases, but it is moving along negative x-axis. That's why momentum is negative and increasing. Okay, like that you can draw the direction. Okay, another one for magnitude of momentum. What is the best idea? Speak up. For magnitude of momentum, this one only. P. What is this one? P square by 2m. That's equal to E minus V of x. Okay. So what is P? Plus or minus root of E minus V of x, isn't it? Sorry, 2m should be there. Plus or minus root of, okay, 2m E minus V of x. Fine. Speak up. Now, what is that E minus V of x in our potential curve? Speak up. That is this one. I mean, at this point, there is no E minus V of x. That is 0. That means momentum is 0. Can you see? Speak up. So when you come to this location, what is E minus V of x? It is keep on increasing when it moves towards mean position. Speak up. E minus V of x keep on increasing. At this mean position, E minus V of x is highest, momentum is highest. Okay. Again, when it moves towards next extreme position, this extreme position, E minus V of x. Are you getting point? This is E, this is V of x. That arrow is the amount of E minus V of x. I mean, this is an energy diagram, right? Y-axis is energy. That under root is deciding P, isn't it? So now, look at here. It will keep on decreasing and it will be at rest at this location again. At this location, again, E minus V of x is 0, isn't it? Now, what you are observing, this E minus V of x, that is increasing highest value and decreasing to 0. And its root of that one also should increase highest value and it should be 0. Okay, speak up. Look at here. Momentum also having the same variation, am I right? From here, increasing highest value and it is becoming 0. Now, observe one thing, okay? This E minus V of x, it is varying in one particular manner, am I right? But here you have positive root as well as negative root. That's why if you draw one of the portion, below one is a mirror image. Are you getting? I mean, so just see this expression. Okay, so P is equal to plus root of 2m E minus V of x. Okay, speak up. Let me first draw this one. okay, that E minus V of x, it was 0 here, highest here, 0 here, I will draw it roughly. Okay, again, one more possibility is P equal to minus root of 2m E minus V of x. Am I right? That means momentum, negative value, okay, negative highest value, again 0. Am I right? I mean, so whatever the phase space trajectory you take, okay, because of this one, okay, I'll just rub it out. Because of this one, I mean, E minus V of x, it varies in one particular manner, but you have positive root as well as negative root for momentum. If you take positive root and if you vary E minus V of x, you will get one curve, okay, in the upper half of the plane. You get exactly same curve in the lower half of the plane, mirror image. You will get mirror image in the lower half of the plane. So that's why whatever the phase space trajectory you take, okay, it has a mirror image along x-axis. Observe that one. Is that okay? Speak up. So now that's what you can observe actually. I mean, these are the observation that you need to make. Okay, whenever we draw the potential and when we choose some energy, okay, energy minus potential energy is a kinetic energy. Am I right? Speak up. That kinetic energy under root, I mean, that will decide the momentum, isn't it? Speak up. What is this one? This is nothing but plus or minus root of 2m into this is kinetic energy, am I right? E minus V of x is kinetic energy. Okay, so that's why. So in the potential curve itself, when you draw the energy, okay, energy minus potential energy is a kinetic energy. You know how kinetic energy varies. That means you know how momentum varies. Suppose in the upper half plane, and you make the mirror image in the lower half plane. That's done. Are you done? This is very strong idea actually. Okay, this expression. I mean, whatever the system they give, first draw the potential. Okay, after you draw the potential, what you do? Speak up. Draw the energy, choose one energy. I mean, you can have your energy choice, am I right? Speak up. Given the system, like suppose here, you can choose your amplitude, isn't it? Speak up. So like that, you choose one energy, okay, then check how what you call kinetic energy varies. What is kinetic energy? This arrow, that is difference between energy and potential energy. So that variation of kinetic energy will be reflected in variation of momentum, okay, increasing, decreasing and all, okay, and you whatever you draw in the upper half, you make a what you call reflection, okay. So you please, screen is already shared, am I right? Speak up. Go to YouTube. Go to YouTube. I mean, some bugs are there here, okay. It is getting off again and again. You go to YouTube. If screen is frozen. I mean, if any problem, you go to YouTube. Okay, speak up. That video, I mean, video camera is getting off. Okay, I mean, it's a Windows problem. Speak up. Are you getting point? So that is one thing. Okay, just by what you call plotting potential energy and then taking some energy level over there and analyzing how kinetic energy is varying if particle moves in the classically allowed region, that will be reflected in the momentum variation. Okay, and another observation that you need to make is, okay, speak up. So as energy decreases, okay, speak up. You can see here itself, am I right? As energy decreases, I mean, this phase space trajectory is going to be smaller and smaller, am I right? So like that, okay, as energy decreases, okay, speak up. Suppose I'll take E3, E2, E1. E1 is less than, E2 less than, E3. Fine. As energy decreases, okay, this phase space trajectory, it will shrink. Here it is shrinking at origin, okay, because origin is our stable equilibrium. It will shrink to the point of stable equilibrium. That point you need to make. Okay, speak up. As you decrease the energy. Okay, speak up. Yeah. Let me save some time here. Like this I have drawn here. Are you getting a point? This is your potential energy. Okay, if you keep on decreasing the energy, what will happen? It will become smaller and smaller ellipse, and it will shrink to the point of stable equilibrium, potential minimum. That observation you need to make. Fine, speak up. Now look at here. Let us go to further idea. Now you have to make points on this one. Okay, these points actually. Okay, what are the things that we have observed here? If you make those points, then it will be very helpful. Okay, speak up. I mean, this is one very strong point. Okay, draw the potential, draw energy, and then check how kinetic energy is varying. That will be reflected in the momentum, and take the reflection below. Okay, speak up. And other one is, okay, observe that, because they are giving the phase space trajectory for various energy, not only one phase space trajectory. Sometimes they are giving only one phase space trajectory, asking what is the direction and all. Okay, sometimes they are giving various phase space trajectory for various energy, and you should know its behavior. If you, I mean, if a potential has a minimum, okay, then it will shrink to, I mean, the point of stable equilibrium. Okay, speak up. So then what else you can observe along with these two? If it is bound particle, phase space trajectory is a closed curve. If it is unbound particle, phase space trajectory is open. I mean, it will not be closed curve actually. That you can observe. Okay. So there is one gate question. I mean, if you try that gate question, okay, you will get to know. Okay, that is unbound particle here. Okay, this question. Okay, I'll pick CSIR net question later. But I mean, I took only bound particle. Am I right? This is bound particle. I mean, particle in harmonic oscillator. Okay, it won't escape, isn't it? So that's why, I mean, this is one type. Other type is unbound, isn't it? So I mean, when particle is bound, phase space trajectory is closed curve. Okay, speak up. And it will shrink to the point of potential minimum. Okay, speak up. If it is unbound, it will be like this. I mean, you can see here, this is this Hamiltonian. If you see, what is this one? P square by 2m, okay, minus alpha q square by 2. In place of x, he took q. Okay, that means v of x or v of q, what is this one? Is equal to plus, so what he wrote? Minus, am I right? Hamiltonian. Okay, speak up. Minus half alpha q square. Okay, what is this potential? If you draw this potential, speak up. It is a downward open parabola, isn't it? It is a downward open parabola, isn't it? So if it is downward open parabola, okay, v of q as a function of q, it is unbound, am I right? Whatever the energy you take here, isn't it? Whatever the energy you take here, suppose you take this energy or this energy, okay, or this energy, fine, speak up. If you shoot the particle, it will come up to this point and it will go back. These are forbidden region, am I right? Pick up. See this one. If this is the energy, okay, so these are the region where potential energy is higher than the energy. Kinetic energy would be negative. Okay, so that's why with this energy, if you shoot the particle, it will come up to this one and it will go back. Or if you shoot the particle from here, it will come up to this point and it will go back. But if energy is greater than 0, okay, then if you shoot the particle, okay, what is the observation? The difference between energy and potential energy is decreasing. What is difference between energy and potential energy? Kinetic energy decreasing. Okay, some minimum value, again it is increasing to infinity, isn't it? Speak up. These are the observation you make. Here nowhere it's a bound particle, am I right? Wherever you shoot, particle will go back to infinity, either plus infinity or minus infinity, isn't it? That's why it's an unbound motion. You can see all four options. Okay, he only made different direction here. Okay, so we have already discussed this one, I think, okay, in the class. Okay, so after this harmonic oscillator, I went to this one only. Okay, one bound motion example, one unbound motion example. Okay, both example you should be able to handle. Fine. trajectory direction is important. Look at here, he made the what you call different. I mean, he gave 4 options. All 4 options trajectories are same, but directions are different, isn't it? Then what you have to do? You just have to imagine you are shooting the particle from negative x-axis towards positive x-axis with some energy. Suppose with this energy, okay? Then what will happen when it is moving along positive x-axis? Its momentum is positive. Momentum is positive, decreasing and becoming minimum value, again increasing to infinity. Okay, can I say like this? Momentum is positive, okay, decreasing, becoming minimum value. Wrong. Momentum is positive, decreasing, minimum value, again increasing to infinity. Isn't it? Suppose if I shoot the particle with this energy, fine. If I shoot the particle with this energy, then what would happen? So from here, okay, momentum will keep on decreasing, okay, positive, but keep on decreasing, okay, it will become one minimum value here. Again, it will go back, reflect back, isn't it? While it is coming, momentum keep on decreasing, having some minimum value, okay. So at this location, what is the momentum value? It is zero actually, completely, because E equal to V of x. Okay, momentum is keep on decreasing. Okay, you can see here, am I right? This is the kinetic energy. Kinetic energy keep on decreasing when you shoot the particle from here. Kinetic energy keep on decreasing, becoming zero, and again it started moving along negative x-axis. Okay, keep on increasing, isn't it? That means momentum was positive. Okay, it is keep on decreasing, it is becoming zero. Then it started moving along negative x-axis. Momentum, I mean, with increase in kinetic energy, it is like this. I mean, those are sufficient to quickly eliminate the option. Okay, like that, you should imagine that you have shooted the particle here. Then the trajectory direction will be easily found. Fine, speak up. When this energy equal to zero, can you guess what would happen? If energy equal to zero, look at here, P equal to plus or minus Q equation will come. Can you see here? If Hamiltonian is the energy here. If it is zero, what is this one? P square is equal to some Q square, some constant into Q square. P equal to plus or minus Q. Those are the straight line you are seeing. Fine. Those are the straight lines. Is that okay? Speak up. I did at least half an hour explanation on this one. So you see this one. Or, so I mean, in NPTEL course, Professor Balkrishnan explained this one very well. Okay, this particular example. Okay, I mean, later it appeared in the GATE exam. Okay, speak up. So, but if you draw the potential energy curve, draw different energy and think. Okay, speak up. How kinetic energy increasing, decreasing. In the same manner, momentum increases and decreases. Okay, while thinking about direction, okay, of the phase space trajectory, you think that, okay, if particle moves in this direction, what is happening? If particle moves in this direction, what is happening? If particle shooted from here, what is happening? If particle is left at any point, what is happening? Isn't it? Now look at here. If suppose particle is at this point with this energy, kinetic energy is zero, but force is not zero. Why? Potential derivative exists, isn't it? What is the force direction? Potential derivative is negative. Am I right? Minus dv by dx is positive along positive x-axis. If you start from here, it is experiencing force along positive x-axis with increase in kinetic energy. It will move along positive x-axis. Are you getting this logic? Speak up. Grab this idea. Okay, this is, look at here, unbound motion. Okay, we don't have any closed trajectories here. Okay, speak up. And one more thing that they may ask here is, okay, for harmonic oscillator, okay, let us take the exam question only, CSIR net question. Harmonic oscillator, but you have a damping, a block of mass m, okay, attached to a spring, okay, oscillates horizontally on a surface. Okay, the coefficient of friction between the block and the surface is mu. That means there exists a friction. Okay, speak up. Then following trajectory best describe the motion of the block in the phase space. Speak up. If there was no friction, it would have been ellipse. Am I right? Pick up. If there is friction, now look at here. He is talking about, if there is friction, what will happen? Suppose if you start with one extreme position, if you start with right extreme position, it will start moving along negative x-axis with increase in momentum. Am I right? It will not go and reach the same point in the negative x-axis. Am I right? It will reach slightly before that one because of the friction. It will lose the energy. Okay, it will reach here. Suppose if it start with this extreme position, it won't reach the same distance after this one, isn't it? Because it is keep on losing the energy. Am I right? It will come here like that. Somehow, so its oscillation will die out to be 0. Is that okay? Speak up. Like that. If you have a what you call damped harmonic oscillator, okay, speak up. If the surface has a friction, okay, if you leave it, okay, so if you leave it at an amplitude a, it won't reach at minus a. It will reach, because of the friction, it will keep on losing the energy. It will reach somewhere here. Then if you start its journey from here, it won't reach the same distance along positive x-axis. Am I right? Suppose if it is x equal to 0. Okay, speak up. That logic is sufficient. Am I right? So if it were what you call undamped, then it will be ellipse like this. Am I right? If you start from here, it will go to the same distance. Okay, minus a. Then it will come back to plus a, minus a like this, isn't it? But if it is damped, okay, or how to say, if it is friction full surface, okay. Wait a second. That damped oscillator is different from friction surface oscillator. Damped means it will be velocity dependent. Okay, that means if suppose you have a frictionless stable spring mass system, if you immerse that one in some liquid, then it's what you call whatever the that opposition it is experiencing. Okay, that will be depending on the speed. That is actually damping. Okay, this is oscillation on a friction full surface. Okay, can I say like this? Speak up. So because of the friction, suppose if it started with a, it won't end at this same distance here. Okay, because of the friction, again starting with here, it won't end the same position here. And we already know this is the phase space trajectory direction. Am I right? Like here. Fine. I'm just continuing. Okay, you just choose the appropriate option here, isn't it? If you start with this extreme position, its momentum, it will start moving along negative x-axis. Momentum is negative. Am I right? This is the direction, isn't it? And another one is ellipse. Ellipse is not possible. That is only for when there is no friction. That is possible. Am I right? So that's why option 2 is right. Are you getting my point? Speak up. Try to understand that one. Then this is nothing actually. Okay, speak up. Then they have asked some tricky question. Okay, now look into this one. This is how easy it is. This is what exactly we were doing. Am I right? He gave potential curve. He gave one energy. Speak up. It's not ellipse. You can remove that one. Okay. So the difference between, at these two locations, momentums are 0. It is 0 everywhere. Okay, in all options. Okay. So here kinetic energy keep on increasing, some high value. Again, kinetic energy keep on decreasing, isn't it? Some lowest value, then keep on increasing to very high value here. Okay, that means corresponding momentum is highest here, isn't it? Again, keep on decreasing to this. My arrow is a kinetic energy. Is that okay? Kinetic energy. That kinetic energy increase, decrease, that will be reflected in the momentum. Am I right? This is the appropriate option. Speak up. Highest momentum appears somewhere here, isn't it? And again, it's a mirror image. Is that okay? So this is what exactly we were doing over there. Fine. Speak up. Just draw the energy, draw the potential, draw the energy, keep on drawing kinetic energy variation. That variation will be reflected in the momentum variation. Kinetic energy increasing, decreasing, increasing to high value, decreasing to zero. Momentum increasing, decreasing, increasing to higher value, decreasing to zero. That's how it is happening. Fine. Now there are two questions, okay? I mean, where you should be quite good at, okay? Drawing the, plotting the curve. Plotting the curve skill is required. I don't know whether you can see this one or not. Okay. Can you see here? V of x is nothing but minus half x square plus 1 by 4 x raised to 4. How do you quickly plot this one? If you plot this one, you can quickly eliminate the option. I mean, you don't have to sit and draw and keep on analyzing. Okay, you will get some. You got some idea now. Am I right? Speak up. You can quickly do that one. Speak up. How do you do this one? Huh?
We can x square and x raised to 4. Then we can analyze where x square is dominating.
Now we need potential minimum, maximum also here. So that's why better to go for derivative idea. Okay, speak up. V dash of x. What is this one? Minus x plus x cube. Okay, V dash of x equal to 0. That is what is that? X cube minus x equal to 0. Be careful. Take x outside. X square minus 1 equal to 0. So then x equal to 0 or x equal to plus or minus 1. Fine. Then go for second derivative. V double dash of x. What is this one? Minus 1 plus 3 x square. Am I right? So what is V double dash of 0? That's equal to minus 1. That means x equal to 0 is maximum. Am I right? Second derivative, negative means it's a point of maximum, isn't it? Maximum. Okay. So at x equal to V double dash of plus or minus 1. What is this one? So 2. Am I right? Plus 2. So that means x equal to plus or minus 1 are point of minimum. This information is sufficient to completely plot it actually. At this point, speak up, at x equal to 0, it has a maximum. Okay. At x equal to plus 1 and minus 1. Okay. Minus 1, plus 1 here, minus 1 here, it has a minimum. What is the potential value? V of x, that's equal to minus half x square. What is that? Plus 1 by 4 x power 4. Am I right? When x equal to 0, okay, value of the function is 0 as well as it is having maximum, then it must be like this. Speak up. I mean, it's all curve plotting skill now. Am I right? It must be like this. Now look at here. When you put x equal to plus 1 or minus 1, okay, what is happening? This is lower, this is higher. Am I right? X square and x raised to 4, both are 1. Am I right? Speak up. So V of plus or minus 1. What is this one? Minus half plus 1 by 4. What is this one? Minus 1 by 4. Okay, that means, okay, it has a minimum value of the function is negative at those points. Okay, it has minimum at these two locations. And there are no other extremas. Just join them. And it should be symmetric curve. Can I just redraw? No, I mean, if it goes and comes back, there comes one more maximum. That information we didn't get. Am I right? It can cross the 0. Why not? I mean, what will happen is this x raised to 4 will dominate after some time. Speak up. I mean, no, you have one minimum here. Do you have any maximum here? No. Then it should keep on increasing. Is that okay? Speak up. It's completely bound particle. Can you see here? If it goes here, it is completely bound particle. When you redraw this one, okay, it's not symmetric here. It should be symmetric. Fine. Now you can observe that one thing is it's always closed curve, and other one is those phase-space trajectories should shrink at -1 and +1. Why -1 and +1 are stable equilibrium? This information is sufficient to eliminate the option. Can you see here? That is this option only, first option only. Am I right? All are, I mean, okay, all, I think all options have a closed trajectory only, but this has some unbound trajectory. Okay, you can eliminate this one, and it won't shrink at x equal to 0 actually. X equal to 0 is an unstable point, isn't it? X equal to 0 is an unstable equilibrium. Okay, so I mean, this potential minimum, okay, at that point phase space trajectory is going to shrink. Now the question is, okay, whether option 3 or option 1, am I right? Both have similarity. Check this out. Speak up. Suppose if you take any of this phase space trajectory, okay, so that will be corresponds to some energy E here, isn't it? Look into this one, kinetic energy, increasing, decreasing, increasing, decreasing. Okay, momentum increasing, decreasing, increasing, decreasing. Okay, speak up. So, but whether this option or option 3, option 3 contain perfect ellipse, am I right? I mean, these are not perfect parabolas. If they are perfect parabola, corresponding, I mean, suppose if you have this energy, okay, speak up. If you have this energy, corresponds to this energy, okay, corresponds to this energy. If I draw the phase space trajectory, I mean, this will not be perfect ellipse, am I right? How can you expect it to be perfectly ellipse? Isn't it? I mean, here he gave perfect ellipse here, isn't it? You can see here, this potential is not parabola, am I right? It is quietly different, am I right? Speak up. That's why you can expect slight variation from the ellipse like this. Again, that also you can analyze, okay, not completely like this, okay, like this actually. But it is not perfect ellipse. Then you can eliminate that option also. Speak up. So grab this idea. Again, ellipse only coming. Like this actually. Okay, similarly. Like this actually. Are you getting fine? And if you keep on decreasing the energy, it will shrink to 0. Speak up. So those are sufficient to eliminate the option. Okay, I mean, only confusion is, okay, this also shrinking at these 2 points, this also shrinking at these 2 points. Which one to be chosen, isn't it? Speak up. It can't be perfectly ellipse. Why? Perfect ellipse happens if it is parabolic curve that we experienced in harmonic oscillator. Then you can choose this option. Fine. Speak up. And this curve will come, okay, this curve, whatever he has drawn, okay, this curve will come when exactly energy equal to 0 actually. Okay, speak up. So it can come up to this point, it can go here or it can move back here. Both options will be there, because when it comes to this point, its force is 0. Kinetic energy is also 0. Okay, speak up. Like that. Okay, there is one more problem. There is one more problem. Again, I'm not going to solve it because this is the same as earlier. What is the main difference? Can you see? Minus k square x raised to 4 plus omega square x square. It is a negative sign on the function that we took earlier, isn't it? We had negative sign on x square part, positive sign on x raised to 4 part. Okay, you have one more negative sign multiplied. That's why what you can expect, if you multiply negative sign to the last curve, what you can expect, isn't it? I just flipped over this curve. Roughly, we need one rough curve here. Fine, speak up. Then what would happen? You have some bound motion possible. Suppose if you have energy E here, okay, here it is unbound, here it is unbound, here it is bound actually. Okay, suppose energy E somewhere here, then all are unbound motion. Okay, speak up like this. Then you can have some logic here. You have some bound motion here, closed curve here. Okay, speak up. That you can choose. That's it. Or I mean, or take different energy, start plotting. You will exactly end up here. Okay, you will exactly end up with this one. Or you can see here. Okay, if I take this energy, okay, what is happening? Kinetic energy decreasing, slightly increasing, decreasing, again increasing. Okay, speak up. Can you see here? Momentum was higher, decreasing, slightly increasing, decreasing, again increasing. Those you can observe actually. Okay, suppose if you have this energy, for this energy there is a bound motion that is possible. Am I right? Closed curve which is possible. Can you see that one? Suppose if you take this one, okay, speak up. This is the energy. If you suppose shoot the particle from the infinity, kinetic energy decreasing, again it is increasing. Am I right? So that is this portion of the curve. Momentum was positive while it is moving along positive x-axis. Stops, then go back. Am I right? Speak up. It is like this. Momentum higher, 0, negative and increasing when it is going back. Can you analyze this one? Speak up. Plot the potential and analyze this one. Okay. Now we have one problem. Okay, which just checks what is your. I mean, once you have this much idea, okay. Next thing is, okay, this problem will exactly check you what is your curve plotting skill. What is your potential? Ax square plus v naught into e power minus 10x. How do you plot this curve? X is? Yeah, that is very good idea. Am I right? Which curve dominates in which area? Okay, that's a good idea. When x is negative, okay, speak up. Exponential usually dominates. Am I right? Speak up. I mean, this is exponentially decreasing curve. Speak up. V of x. Okay. When x is positive, this is quite low. Am I right? It is almost parabolic, isn't it? When x equal to 0, it is having some positive value. Okay, speak up. So that's why. So okay, let me first draw that exponentially decreasing function. Okay, then I will draw my parabolic function. Can I draw like this? Okay, parabolic function will be like this actually. Can I say like this? Speak up. So when x is less than 0, where exponential is more sharply increasing, okay, it is following exponential. When x is, speak up, greater than 0, it is following ax square, parabolic nature. Are you getting my point? It will be, I mean, I need to make this one more sharper actually. Okay, this should go down, am I right? Ax square should go down. So this is like this. Okay, speak up. It will be like this actually. I should make it more wider. Okay, I should make this one more sharper. Are you getting my point? Speak up. Like this, then this is slow increase actually. Now you can do the derivative test also And you can observe that you have one minimum at positive x value. That also you can observe. For this curve, okay, you can quickly do the derivative test. Am I right? Speak up. What is that? Suppose, okay, it is roughly having this curve, you know. Okay, where this minimum comes, am I right? That from that we can answer that one, am I right? Where it minimum comes, isn't it? Speak up. So for that, what you can do? You can have derivative test also actually. I mean, if you do that one, that's better. So v dash of x, what is this one? 2ax minus 10 v naught e power minus 10x. Okay, so equate v dash of x to 0. What you get? 2ax, that's equal to 10 v naught e power minus 10x. Speak up. This equation is possible only for some positive xy. Right hand side is positive, am I right? I mean, this is one transcendental equation now. Transcendental equation. One side exponential, one side linear. How do you solve this one? You have to plot this one, find the intersection actually. Okay, anyway, but logically you can get this equation is, this equality is positive because this cannot be negative, am I right? For some positive x value. That means you have one extremum at positive x value. At least that you can, what you call, observe here. Speak up. So that's why, I mean, once you plot this one, okay, once you plot this one, let me plot it one more time, okay. So it is sharply increasing here. Oh, and it will slowly increasing here. Are you getting point? This is what I was trying to plot. Because this exponential is quite sharp. E power minus 10x is there, am I right? Speak up. In the negative x-axis, okay. But what is this? Your parabolic nature? It is quite slow, am I right? Compared to exponential, okay. That's why that difference should be seen actually in your curve. And you have a minimum, okay, at some positive x value, okay. So this is your v of x curve. Fine. If this is your v of x curve, let us take one energy. Let us take one energy. Speak up. Fine. This is your p x here. Now, when you see the option, you need to observe very closely here. Okay, when you see the option, look into this option. I mean, you can quickly avoid these two. Am I right? How ellipse can happen? Okay, you can quickly avoid these two. Okay, but among these two, you have question. Am I right? Pick up which one you choose. Huh? Why option 2?
While going, it's reaching maximum value in less time.
Faster or something. Exactly. What I see is, okay, what I see is, if I keep on shrinking this one, okay, if I keep on shrinking this one, it will shrink at some positive x value. That is where I have potential minimum, isn't it? I mean, he didn't give, I mean, many curves here, but if I keep on shrinking this one, it will shrink somewhere here. If I keep on shrinking this one, it will shrink somewhere here. That also okay to eliminate the option. Because, I mean, that curve should shrink at the point of stable equilibrium, potential minimum. Okay, as you told, I mean, that is one logic, okay, to eliminate the option. Okay, other logic is, okay, speak up. Other logic is, as you told, look at here, from here to here, okay, your kinetic energy, speak up, changing quickly. Can you see here? I mean, it is increasing quickly. But here to here, it is taking more distance for kinetic energy to decrease to 0. Are you getting? So that's why from here, kinetic energy is quickly rising. I mean, suppose if you start from here, kinetic energy is quickly rising, but it is taking more distance here for kinetic energy to decrease to 0. That is sufficient, isn't it? That is sufficient. and mirror image we already discussed. Am I right? I mean, I'll just draw above part. Below part is a mirror image. Speak up. I mean, two ways to eliminate the option. One is I observed that it has a stable equilibrium at this point. That's why it should shrink over there. Okay. So this one, what is this? This one is appearing to be shrinking at positive x value. This one appearing to be shrinking at negative x value. That's how I have chosen. Or when I closely observe this one, this is not symmetric potential. Am I right? Pick up. So it is taking less distance to increase. It is taking more distance to decrease. Isn't it? So that's also sufficient for me to choose the option. Fine. This option. So ultimately, once you understand this technique, drawing potential and then drawing the phase space trajectory, what happens? It all becomes your curve plotting skill. I mean, if you draw the potential, it's done. And you don't have to analyze fully, you just have to analyze enough to eliminate the option. Fine? Speak. I mean, these are CSIR net question. You have more gate question for practice. Okay. Suppose this one, particle bouncing. Okay. I mean, you take energies conserved here. Okay. Speak up. Elastic one. Speak up. From gate exam. This is one more. Fine. Speak up. You make it more steeper, you make it slightly wider. Okay, this curve. Okay, then it would be appropriate. Need to make this curve more steeper. Fine. Yeah. Any question on Google Meet? Speak up. Have this technique. I mean, when I see this one, okay, this particular question, where is it? They're expecting this way of analysis only. Whatever the way this we have done, isn't it? When I see this question. Yeah. Okay. On Monday morning, I'll pick Hamiltonian dynamics more question, and I will pick some canonical transformation question also. Okay. Revise Hamiltonian dynamics as well as canonical transformation. Okay. Poisson bracket relations and all. Okay. Along with Poisson bracket relation, you better to practice your quantum commutation relation. Isn't it? They are closely related. Am I right? So you better to practice some quantum commutation relation along with Poisson bracket. Okay, which will, I mean, make our quick, I mean, we can solve some problem quickly actually. Sometimes they'll ask some conservation quantity, am I right? Then you need to check Poisson bracket relation. Okay, you should be very quick in article finding that Poisson bracket relation. Okay, speak up. So practice of that one also. And only Poisson bracket relation, that may be separate question. Okay, in the exam. Fine, speak up. Any question? Okay.
Sir,
Huh.
sir, yesterday we were discussing a question on central force. In which you said that
angular momentum is conserved. So why I took that one? Because in one just a TFR question, so they gave like this. Okay, one suppose one satellite changes the one orbit to other orbit. Okay, there they gave that angular momentum is constant actually. Okay, in that particular problem, they didn't mention anything. Okay, what they said, G is changing. Am I right?
Yes, sir.
G is changing means, okay, in your V of R, okay, minus K by R, this K is changing, isn't it? Whether angular momentum conservation depends on this K or not. Okay, let us try to grab this one. How does angular momentum conservation came? L is equal to half m r dot square plus r square theta dot square, okay, minus of minus K by R. Am I right? Here theta was cyclic. Then p theta, that's equal to dou L by dou theta. P theta is angular momentum. Motion is restricted to plane. Okay, that motion is restricted plane. That argument is from angular momentum conservation only. Okay, then we go for two-dimensional motion. Okay, be careful. So that's equal to m r square theta dot. That's a constant of motion. We wrote it as angular momentum. I think nowhere here, only mass comes, G won't come, okay? This won't play the role, am I right? This part in this conservation law. What do you mean by anything is conserved? If you start with that quantity will not vary at any later time. I mean, that is the conservation law, isn't it? When I see this equation, I mean, yesterday I thought of this one, but I mean, I didn't find any reasoning in the book actually. That's why I didn't pick it up again. Okay. But what I'm seeing here is, okay, so nowhere here this is playing the role. Am I right? This K contains our gravitational constant. Am I right? Only mass may be playing the role. Okay, if mass of the satellite or planet, okay, if that changes, then don't apply conservation of angular momentum. I mean, because mass is coming here. Okay, but mass of the earth he kept as it is. Am I right in the problem? He changed G. G means, I mean, this is the one. Am I right? Minus G. What he took, satellite sun or sun and earth? So, sorry, satellite earth or sun and earth? Satellite and earth actually. Okay, speak up. Mass of the earth, mass of the satellite divided by R. Am I right? Hmm? What you're saying? So why do you write that one? Because you are keeping that satellite mass constant, am I right? In the problem. Energy will change. I mean, it's a conservative system. If you write corresponding Hamiltonian, okay, this is playing the role. Energy will change. Okay, speak up. Let me check some other book, okay, other than whatever we are referring. Okay, speak up for this one. And one more, I mean, I will teach, okay, before next JAM exam, that Kepler third law, writing in the angular momentum form. Okay, they are expecting that one. Okay, speak up. You are saying any other questions? Speak up.
Sir, that you can practice more questions for this central force related problem.
Yeah, actually, I yesterday I kept some question. Only one question I need to work on that one. Okay, rest of the question I worked already. Okay, I mean, only from CSIR net I picked the question. Okay, speak up. So you either, I mean, if you are in the course, you can visit those quizzes. Okay, speak up. Did you guys solve this problem? What you have to do? V effective, that's equal to minus K by R minus K dash by 3R cube plus L square by 2M R square. Now you have to put the condition that, okay, so it should have a minimum take first derivative, equate to 0. Okay, take second derivative, substitute the point of first derivative 0. Okay, that second derivative must be greater than 0. That should lead to this one actually. Okay, speak up. Then only you can have a stable circular orbit. Stable circular orbit is possible only when V effective has minimum. Okay, in Ghostin he worked out very simple potential like V of R is equal to some kr power n or something. N is greater than -3 or -2 he proved actually. But that won't work here, am I right? Speak up. Look into this one. He gave some different potential. Okay, it's purely derivative. This particular question. Okay, speak up. So check this out. If you couldn't solve, you have to ask me. Okay, in the instruction channel, you can ask me. I will try that one. Okay, speak up. I think the rest of them are okay. Am I right? Speak up. Yeah, this one we solved. Am I right? This one we solved. Okay. Now, if you need more problem, okay, you pick either quizzes on our course portal, or you can pick our what you call free resources. Okay, in that one topic wise question. There also you can find that one. Okay, central force problem separately segregated. Okay, speak up right now. Okay, I mean that's the right way. I mean what he's asking, more problem. Okay, only solving previous problem is not sufficient. Okay, you have to solve very new problem, whether you can apply your concept and get it done or not. Okay, that you need to check. Okay, so while taking quiz, not only take previous questions. Okay, speak up. I'm solving previous questions so that you build some confidence. It's not because that those will appear in the exam. Okay, speak up. Pick some more question and pick our designed MCQs. Okay, those who are in the course. Okay, I try to touch different aspect whatever given in the Ghostin textbook. Okay, in that our design MCQ. Fine, speak. Still one more question is there. I'll check. I'll try to pick it in the next class. Okay. Yeah. Any question? Any other question, Bharat? Yeah. Speak up. Okay. So